Hi, my name is Allister. I'm going to be talking today about a functional EDSL for mathematics visualization that compiles to JavaScript. Just a little bit about me. I've been a .NET programmer for quite a long time now. Just been an F# programmer for about 5 years. I'm currently an economics student at the University of London's EMFSS program, and I'm interested in all aspects of open source mathematical computing and how software languages are used in math education. So I'm going to talk about Sylvester. Sylvester is a functional EDSL for mathematical computing. It aims to provide a unified notation for symbolic, logical, visual aspects of mathematics, and to provide a unified functional language interface to different open source tools libraries. Probably heard of these tools: Maximo, Z3, JSXGraph. So what does it mean to provide a unified notation, a unified functional language? Well, let's get into our first demo. And we can just look at what Sylvester is trying to do. Okay, so we can first look at some symbolic operations. Okay, so we open our Sylvester namespace, and we declare two real symbolic variables, and we're going to be using these two symbolic variables throughout our demo. Okay, so we can do things, we can express different math operations, symbolic math operations, or we can do things like algebraic expansion, simplification, partial fraction expansion, okay, trigonometric expansion, trigonometric reduction. Now, here we're defining a function of one real variable, okay, and we can do the typical operations. We can differentiate and integrate on that particular function. Okay, now Sylvester uses maxima by default for its symbolic operations. Okay, so we can just look at the output of maxima. So as we're going through the demo, Max is going to be processing these symbolic operations. Okay, so what we're doing is we just provide a functional language interface over maxima. Okay, so basically, instead of using the maximum native language, we can use F# DSL to do symbolic operations. Okay, so let's look at some linear algebra operations. So we define a 2D vector, and all objects in Sylvester by default are fully symbolic. So as we're doing operations on linear algebra, they preserve the symbolic form. Okay, so just we're doing addition, just taking the inner product. Okay, and same thing for a matrix. Now matrices use number-dependent types, which lets us express the number of rows and columns in a matrix as part of the type. Okay, so we can define a 3x3 matrix here, and well, we can do things like just simple algebraic operations on the matrix. We can do things like elementary row operations. So these operations are very, very common in linear algebra. So things like multiplying a particular row by a scalar, or switching out one row with another in a linear equation system. This would preserve the linear equation system. We can create an augmenting matrix, so we can augment that matrix by adding a vector to it, and that vector becomes one of the columns. Now we have a 3x4 matrix. Now, because that's using number-dependent types, if we look at this particular operation, this isn't conformable. So n by m isn't conformable for multiplication in this particular order. So if we try to execute this, it actually gets a type error because the two aren't conformable for multiplication. Okay, but in the other order, then this is okay. So these two are conformable. Okay, so this is okay. Okay, so we can look at some, so that's the solver operations. So we can use Sylvester. Maxima has a pretty good linear equation solver, and we can use Sylvester to express a linear equation system and just solve this particular equation. So Maxima can solve this pretty easily. We can also use Z3. Z3 is an open source SMT, satisfiable modular theorems solver from Microsoft. It's really, really popular. And Sylvester provides a functional language interface to Z3. So here we're expressing a particular optimization problem. We want to maximize the area of a rectangle, given that the perimeter of the rectangle is 100. So this is how we express that in Sylvester. And we can solve this pretty easily using Z3. Okay, so here's the same optimization problem, but we've added some more constraints. Okay, we have that we set r equal 5, and we use another constraint, and Z3 can solve this pretty easily again. Okay, so note that we're using this double equal sign operator, so I'll come back to that when we look at the logical operations in Sylvester. Okay, so if we look at, so let's look at logical operations. So Sylvester comes with its own proof assistant called Sylv. So we have a theory of real numbers. Now, remember I said that we were using the double equal sign operator. Now, we have the standard F-sharp equality operator. These two expressions, they're not the same expression because they have the symbols in different form. Okay, so this is actually false. It's not true that these two are the same. But we know that in the theory of real numbers, those two expressions are actually they're actually equal because real numbers are commutative, right? So this particular expression is actually the same. So what we can do is in Sylvester we can express, okay, that our real number theory, whether or not it says that this particular expression is equal. And in this case, it actually is. So this is true axiomatically. Okay, so if we try to just create a theorem from this expression, then yeah, this is true axiomatically. Okay, so Sylv tells us this is true because of the theory, the axiom of commutativity. Now, Sylv is an ML proof assistant, so we can't construct theorems without incompleteness. So if you look at another expression, this particular expression, in order to show this is true, we actually need a proof. We can't construct the theorem like this because we don't have a proof of this. Okay, so to construct this theorem, we need to provide a proof. And this is a really simple proof. I mean, we're just applying commutative rule on the left-hand side. But once we have a proof, that's when we can construct, that's the case that we can construct a theorem. And theorems, I mean, this is a pretty simple theorem, but theorems can range from, the theories and theorems can range from the entire range of mathematical domains. I think from real analysis, linear algebra. There's no limit as to what sort of theorems you can express and prove using Sylv. Okay, so we looked at the symbolic and the logical operation Sylvester. So let's look at the visualization aspect of Sylvester. That's what we're going to focus on today. Okay, so here we're going to we just want to visualize that function that we defined before. We just want to visualize f. Okay, so this is how we visualize f, that functions in Sylvester by default. We just use it as a simple draw command, and we say we want to use the defaults. Now, if we want to use just have user specified properties, so here's how we do it in Sylvester. So when we draw it like this, basically we're specifying that we want the x-axis range to be a particular value, and we want the y-axis range to be a particular value. So this is how we just simply, so what we can do is we can customize how the visualization is rendered using parameters we pass to the draw command. Okay, and so here we're defining another function, sine function. In this case, we have a real constant called a, and we define a function in terms of that. And what we can do is we can say, okay, when we're visualizing f, that particular function, we want to set a to 1. Okay, so here's where we just set a to 1 and we visualize it. And of course, so we can just specify what value we want for that particular constant in our visualization. And the visualization will render because of the properties that we set. Okay. So here we're using a more complex set of properties. Okay, so we're going to specify the x-axis range. What we're going to do is we're going to say we want to use an interval for that particular constant a. Okay, and if we use an interval, we have to specify the range of the y-axis, because once the axis is rendered, it can't change. So we need to specify by default what the range is going to be if we're going to use intervals in our visualization. And we're going to say, okay, we want to have a red plot, and we're going to increase the stroke width of the plot. So we can draw. So this is what we get when we render using those parameters. So we have a slider here, and we can use the slider basically to increase the value of that particular constant a. And this would just change it dynamically, the visualization. Okay, so this is a more complex. So, but I mean, even though it's a more complex visualization, the syntax is still relatively simple. You don't need to use JavaScript or anything like that. Just to get this sort of interactive visualization. Okay, and we can also visualize things like vectors. So here we're defining a vector, and we're going to say that we want to draw. We want to draw basically another vector. So let me render this. Okay, so what we've done is we're looking at a vector. So, and we define the constants. So the vector is a symbolic vector, and we say that we want to range the constants. We want R to be 1 to 9 and S to be 5 to 10. So we can just use our sliders again just to change the value of that vector. And of course that happens in our visualization. So that's example. So basically the goal is that any object you can express in Sylvester, by default, you'll be able to visualize it using that draw command. Okay, so we looked at visualization of Sylvester. So why Sylvester? Let's now talk a little bit about what motivates developing yet another mathematical language, yet another programming language. Well, if you think about what's the role of computers in math practice and education today, you think of high school students doing homework, or college students working on a proof or for an assignment, or researchers working on a paper. And I mean, the thing was that what we use computers for, well, of course, we use it for numerical calculation. We use it for reference material lookup. We look up on Wikipedia, we look up on textbooks. For communication, I mean, talking with others, talking with our instructors, doing things like document management. But I mean, if you think about the core practice of math, what we do, computers and software, they aren't very central. I mean, you can basically do math completely without using computers and software. That's how that's if you're growing up, that's how a lot of us actually did math without having to use computers. Okay, today students use computers as devices for numeric computing, or for things like communication and reference lookup. And the numeric capabilities of computers are very accessible. Okay, that particular be able to calculate numbers is very accessible. But those other capabilities, like the symbolic, logical visualization capabilities, they're not really that accessible to end users. Okay, and I think that's one of the reasons why, even though computers and software, they've altered the core process of things like business. So today, things like accounting, stock keeping, you wouldn't think that you could run a business or do business today, without really like using computers, running a large business anyway. But that's not really true with mathematical education. I mean, today, even though of course there are a lot of differences, but I mean, fundamentally, a lot of things that we do are still the same as we did, centuries ago. Okay, so computers really haven't altered the core process of math education and practice. So, well, what's the reason for Sylvester? So basically, the question is, can we make computers and software become fundamental to math practice and education? Okay, and so right now today, for the software for higher mathematics, we have computer algebra systems and we have theorem provers, and it's kind of split between these two generally categories of software. So what Sylvester tries to do is it tries to give you a syntax for expressing these different aspects of mathematics, a single language, a single interface for doing all these things. So basically, so you can have a single language and a single environment, like Jupyter notebooks, where if you're solving university level math problems, you can have a single language to be able to do that. And of course, as the language develops, to be able to go beyond that, to if you're doing research, that's sort of the broad view of Sylvester. To have a single language and a single interface for doing higher mathematics, and to try to make computers and software really central to the whole math practice and education today. Okay, so so we can focus. Let's just focus on the visualization aspect of Sylvester. So Sylvester, we saw that there's a high-level API around that draw command, where you can just draw mathematical objects and you can set parameters using that particular syntax. Now, there's also a low-level API, and this is a functional interface to JSXGraph, where you work with objects. Instead of working with mathematical objects, you work with objects like points, lines, polygons, all the different elements of interactive visualizations. Okay, so JSXGraph, it's a cross-browser JavaScript library for interactive geometry. Okay, so that's really, so all the visualization that we saw before, they were rendered using JSXGraph. Okay, now JSXGraph is really designed it was really designed to be embedded in web applications, or applications like Moodle, and the target audience was really web developers. So what Sylvester does, it provides a functional language interface to JSXGraph. So that's the low-level visualization API, and from that low-level API, what you can do is you can build higher-level visualization functions. So we can just look at the low-level visualization API. So I'm just going to switch to out of presentation view for a bit, just so we can look at the code and see how. So this is an example of using the low-level visualization API. So this is we're just defining another function, and we're going to be using. So these are all JSXGraph objects. We have boards, we have sliders, function graph. This is a Riemann sum. So if we run this, and you can see it's all basically F# code. Okay, so what happens is that when we define this code, we define it inside the F# quotation. And defining this in an F# quotation, it signals to the Jupyter kernel that this F# code should be compiled to JavaScript. So when we run this particular code, this code gets automatically compiled into JavaScript. So this particular code gives us this visualization. Okay, so this is just a rerun some visualization. Okay, and we're using sliders again just to define different parameters, the endpoints and how many strips we're using in our integration. Okay, so here's another example of using the JSXGraph interface. In this case, we're actually doing 3D. So this is a 3D line. So JSXGraph has 3D capabilities as well. So we can also visualize things like 3D vectors. Okay, so again, we're just using the functional language interface just to define a simple 3D visualization. Okay, so this is a more complex visualization. This is a Euler circle, but again, it's the same thing. We're using just F# code, and again, the F# code, compared to JavaScript, the F# code, I mean, it has a very, very minimal syntax. We're using mostly plain English. There aren't a lot of really semicolons and that sort of thing. So it's in some ways the F# code is a lot simpler to understand than the equivalent JavaScript code. Okay, so if I run this, so this is just a basic Euler circle, and of course, inside of this, it is also interactive. You can manipulate the points. So that's how basically you can use sort of like the low-level visualization API of Sylvester to create. So one of the functions I want to focus on was how do we create this visualization. So we're going to look at creating this particular visualization. Okay, so this is a visualization of an economic function. Okay, so we saw how we visualized functions before. So in this case, what we would like to do is we would like to use a low-level API. When we have more, if we have custom visualizations, or we want to really to be able to control at a low level of the visualizations, we can switch to the low-level API. So just briefly going through it, we're defining a grid as to this is what our graph is going to be. We're defining an x-axis, y-axis, just the labels, and we're defining how things like the stroke width. So we're setting those properties for that particular our grid properties on the board, and then we're defining our sliders. We define what the slider name is, what the range is, where they're going to be on the board, and so then we define our functions in terms of the sliders from the value. So as we change the sliders in this value, of plot chain of visualization changes. Okay, and again, we're using this just typical functional language interface. So again, in many ways it's a lot easier to define these things rather compared to JavaScript. So once we have all the elements we require, we just render that to the board, and this is the output that we get. And all of this is done. All of this is done inside Sylvester. We don't have to switch to JavaScript to be able to do this. Now, given that we've done this in our low-level API, we can define a high-level API. So we can define a high-level type called, let's say, market equilibrium, and just using those elements. And what we could do is we could say, okay, if I want to be able to draw this, I can just use that low-level code we just had to implement the draw member. Okay, so this is how we would implement it. And once I've done that, basically, I can use draw, that same draw command, to be able to just draw simply marked equilibrium, to be able to create visualizations like this using user-supplied parameters. Okay, so this is an example how we can use the low-level API to compose a higher-level visualization API that users can access pretty easily without having to really understand the low-level visualization API. Okay, so and if we're talking about comparing Sylvester to other visualization languages, so of course there are a lot of different visualization languages, but if we compare Sylvester to that's one of the things that really it strikes. Well, so some of the things you consider is like, okay, how easy is the code to understand? How easy is it to grasp, especially by new users? Things like, static types. I mean, these things they help users avoid mistakes, but the key thing is the reusability and composability. Can users easily create higher level types interfaces from lower level types or functions and procedures? that's something that I think is really missing from most visualization languages and libraries today. And of course, well, kind of use interactively, like so certain languages like Metapose, you can't really use it you can't use it interactively. They're not really for creating interactive visualizations. Okay, so and so this is just like some JSX JavaScript code. And I mean, it follows the Sylvester visualization API. It's very close, but you can say that it's might be easier. The Sylvester might be easier for a new user to understand compared to the JavaScript, because JavaScript was created for developers. Okay, for web developers, it was really created for interactive use. And of course, well, Metapose is a really powerful visualization language for creating typeset static documents, but it's not really designed for interactive use. And well, Mathematica is a really popular commercial computer algebra system. And so you can see Mathematica, it's not very long it doesn't take very long to create a visualization like what we saw. But in terms of composability and reusability, obviously I think Sylvester has it's really advanced. Like there's no real way there aren't really advanced scenarios to create like compose higher level interface out of mathematical code. So that's one of the areas where Sylvester is a lot better than, say, Mathematica in terms of visualization. Okay, so that's basically a demo of Sylvester. For more information, you can check out the project on GitHub, or you can get me on Twitter at Allister Beharry. So thank you.